SwayamPrabha. Digital India. Educated India.
Welcome to lecture number 21 of the Statistical Thermodynamics courses for engineers. We're going to have companion tutorial sessions on spherical coordinates, on the linear Hermitian operators, as well as on eigenvalues and eigenfunctions. And we are also going to have a brief idea about the ODEs, the different forms of ODEs, because we are using some of them. So this will be mainly as a recap or recollection of the courses that you have taken earlier. So far we have, as we know, we have done an extensive piece of work in analyzing the rotational energy mode and how is it represented by the Legendre's polynomial. Now let us consider a rigid two-particle system. So assuming that this is the two particle, this is R, and we are assuming that this R is fixed. All right. So this is rigid rotor. Rotor is undergoing rotation at omega. All right, so this is a rigid rotor, therefore undergoing rotation omega. So we are still in the rotational analysis, if you recall. Okay, so K being the kinetic energy is given as L squared by 2I, where L is I omega. Okay, so L is angular momentum. Okay, I is also given as mu R squared, where I is the moment of inertia. And mu was the reduced mass. This part was well understood before. Okay, so A operator for the kinetic energy is basically square by 2 mu into this, which is say square by 2 mu 1 over R square d by dr square dr plus, so this is continuous, 1 over R square sin theta d by d theta sin theta partial theta plus 1 over R square sin square theta square. That was the total expression, to recall. Okay. So for a rigid rotor, R is invariant. That means it is fixed. So the K operator therefore becomes, so there is no differential with respect to R anymore. H squared by 2I, right? 1 over sin theta d by d theta partial theta plus 1 over square theta partial square, that is this. Okay, R is invariant for most molecules. It's invariant for most molecules. molecules, not showing any vibrational motion, not showing any vibrational motion. All right. So that is what it is. Okay. So therefore, this operator L hat is equal to minus h bar square. Okay. 1 over sine theta d by d theta sine theta d by d theta plus 1 over sine square theta d square by pi square. All right. So remember, this was the I omega. L was I omega. So this is the operator, or the quantum mechanical operator for L. Okay. So apply to the spherical harmonics. Apply to spherical harmonics. What were the spherical harmonics? Let us just recall that the spherical harmonics, these were the spherical harmonics. Okay, so we apply the operator to the spherical harmonics. Okay, so it is L hat square applied to y theta comma phi is equal to minus h square. Okay. Okay. 1 by sine theta d by theta sine theta dy by theta plus 1 over sine square theta y square equal to alpha h square y. All right. So in other words, or h square y j m theta comma phi, okay, is equal to j into j plus 1 h bar square yjm. So multiply by r, we have u internal is equal to j into j plus 1 h bar square chi internal r theta phi. All right. So so that is what it is. So this R is basically was the from the separation of variables that we did earlier. Okay, so this was what it was. So therefore L square bar equal to j into j plus 1 to h bar square. So this is the angular momentum of a rigid diatomic molecule. Okay, is quantized, and the energy of rotation, assuming it's a rigid rotor, is j into j plus 1 by 2i h bar square. Okay. In wave number units, wave number space, basically wave number space. Okay, you can write it as fj is e rotation divided by hc is j into j plus 1 into pe. where j is equal to 0, 1, 2, da da da. Okay, and VE is h divided by 8 pi square, okay, pi square 2e, sorry, h pi square, e, where IE is equal to mu RE square. Okay, we will take a look at what it is. So IE equal to mu RE square. Now this is the equilibrium. RE is the equilibrium, okay, internuclear distance. Internuclear distance RE for molecule, okay, which is behaving as a rigid rotor. All right, got it. Okay, now m is equal to 0 plus minus 1 plus minus 2 da 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 to j. So the degeneracy or the G rotation is also called the rotational degeneracy. Rotational degeneracy is given as 2j plus 1. So that means the above degeneracy corresponds to 2j plus 1 different values of angular momentum, okay, along the z-axis, something like that. So this is what we have. So let us see if there is anything that I missed. The diagram. So let's see on the z coordinate. The z is basically the z component of the angular momentum. Okay, so for say z equal to 2, or z equal to 2, let's do it this way. So let's show it with a simple figure. So say this is the z-axis. Okay, so and say the LZ. So L equal to mh bar. It is like this. So this is basically L j plus 1 h bar. Okay. So this is how for 2, if this is actually equal to 2, then you can have so let's do basically probably a problem to validate some of this. So this is how the quantization occurs along the z-axis. Okay, so the z component of the angular. So this is if you look at figure 6.2 from the book, you would get a much fairer idea. So it is like this: L equal to root over 6h bar. So therefore we have okay. So this is minus h. This is minus 2h. This plus h. This plus 2h. Okay, so this is how the degeneracy part actually happens. It's 2j plus 1. As you can see that there are 5 degeneracy level here. J is equal to 2 basically. Okay, so 2 plus 3, so j equal to 2, and this is how the quantization has actually happens. So I think this is a useful way of showing that what the degenerate levels are. Okay, so this is for a rigid rotor. We have found out that what will be the corresponding degeneracy levels. Now you are going to go and take a look at the vibrational energy mode. All right, the vibrational energy mode up next. So we have still the R component when we separate it to two. So this is d by dr square dr by smaller plus 2 mu r square by h bar square the internal minus vr minus j into j plus 1 into r is equal to 0. Right? So this is the internal energy. Okay. Of all moving electrons in a molecule. Okay. Not a single R coordinate per se. Okay. So separate the electronic and the nuclear motion. We can separate the electronic and nuclear motion. Okay, using Born Oppenheimer approximation. Okay, so that means obviously the mass of the nucleus is much greater than the mass of the electrons. This we know. So the electrons are rapidly moving. So electrons are rapidly moving, okay, and cover many orbits, okay, during a single vibration and rotation of nucleus. Nucleus. Okay, so the internal therefore is written as electronic into rho vibrational, rotation vibration. So this is rho vibrational, rotation and vibration. So this is the Hamiltonian for the electronic. This is electronic is equal to energy electronic into the wave function. And then of course you have the rho vibrational multiplied by the rho vibrational wave function. This is rho vibrational and RV. So, and of course the internal energy is written as E electronic plus E rho vibration. Okay, so now if we do this, the radial portion of the Schrodinger's wave equation becomes. So the radial portion of Schrödinger wave equation, okay, that becomes dr square plus 2 mu square h r square. Then I'm writing whatever goes in the bracket, E rho vibrational minus Vr h bar square by 2 mu r square. This is 2 mu r square j into j plus 1 r equal to 0. This part accounts for electronic motion, or electronic motion. Okay, so this part accounts for the electronic motion. Okay, so now further, E rho vibrational is written as E rotational plus E vibrational. Okay. All right, so therefore d by dr, r square dr by dr is 2 mu square h bar E vibrational minus vr into r is equal to 0. This basically includes electronic energy. Yeah, equal to electronic. Okay, so since electronic R provides the internuclear potential, E rho vibrational is E rotation plus E vibration. Okay, so VR needs an expression. At this point, we need to have an expression for VR. Okay, so VR, which is basically nothing but that includes the electronic potential, needs an expression. Before we move any further. Okay, the most popular choice okay, is called the Morse potential. Is Morse potential. Okay, so Morse potential is something like this. It is written as VR is equal to dE. We'll come across what dE is. 1 minus E minus beta R minus RE. RE, remember, is the mean, the equilibrium internuclear distance is square. So dE and beta are basically two fitting parameters. Two fitting parameters. Okay, RE is the internuclear distance at thermodynamic equilibrium. RE is the internuclear distance at thermodynamic equilibrium. Okay, so let's look at this. So this is VR. Draw a line. Sorry. Okay, so this is RE. This is basically your E. Put it that way. So you need a fitting parameter essentially for this internuclear distance, right? So the Morse potential, basically, what does Morse potential actually mean? So Morse potential, okay, physically represents the chemical bond. Physically represents the chemical bond. The chemical bond. Right? So that is so, but it is hard to deal with. So people adopt something which is a little bit easier to handle. So people adopt okay, the harmonic oscillator potential, which is easier to handle, so to say. Okay, So it is much easier to handle. So VR is therefore written as half K naught R minus RE square, is K is like a spring constant, force constant, right? So this is like a force constant, okay? K naught, which comes from Hooke's law. Hooke's law. Okay, so Hooke's law means K naught is now given as mu 2 pi r square. Okay, so this is actually related, to the oscillator frequency. Okay, so the harmonic oscillator matches with the Morse potential. So this harmonic oscillator, okay, matches with Morse potential. When R is closer to RE, so around the equilibrium intermolecular distance. So if this is that, so this is the Morse potential. Okay, harmonic oscillator will be somewhat like here. So in this zone, which is around RE, it is going to be valid. So RE plus epsilon, okay, on R is less than, so something like that. Okay, so this is valid. Okay, so what we can see is that if R is less than RE, the force is repulsive. Right, when you go to this direction, the force is repulsive, and R is greater than RE. When you go in this particular direction, the force is attractive. Okay. And as R goes to infinity, then we reach dE, which is called the dissociation limit. That means the bond is broken. Dissociation limit. The bond is basically broken. So if your VR is less than dE, we have stable bond. Okay, between two nuclei. You understand the thing, right? So here it is repulsive, here it is attractive. So if you go beyond a certain level, right around here, okay, it is lead to dissociation limit. So normally when your VR or your potential energy is less than dE, remember is that value, is actually much less than dE, we have a stable bond between two nuclei. So when you supply excessive energy, what happens is that you carry the risk of dissociation. And we are dealing with a harmonic oscillator which only agrees within a small space around this equilibrium internuclear distance. And that is represented by essentially a spring constant type of thing. So, and this is required because we need an expression for the potential function. Okay, so in the next class we are going to see where this actually leads us. Okay, in the subsequent chapters, in the subsequent classes we will see where does it lead us. Thank you.